Hello, operating systems people. This is Gabe again, and I'm going to talk about the somewhat dramatic topic today of how in system design we aim to constrain the chaos of the underlying system. Operating systems, from one perspective, essentially provide abstractions to applications. This is one of their main goals. Some would say, and I would say, that they have two main goals. One is to provide these abstractions, and these are the abstractions that applications use to actually access the abstract system resources. And then secondarily, operating systems interface with hardware resources. And in interfacing with them, they multiplex them, right? This is the notion that if we have a finite set of resources on the system, memory, CPU, I/O sources, and we need to allow multiple applications to be able to access those resources. Therefore, we are multiplexing them. However, systems in general do a lot of these things. And one of the main purposes of providing abstractions is actually to manage system complexity. So the idea that as systems grow large, think data centers, think distributed systems, this complexity of the system gets immense. And we need some way to manage that complexity because in the end, human brains can only think about the code that lies in front of them, right? So the big question that we're going to be investigating in this lecture is simply how we constrain complexity and what principles might underlie this. And the perspective I really want you to have here is that we end up having systems that are huge, right? The system that I'm running this presentation on, that you're watching it on, has over 50 million lines of code executing on it, most likely. And how we can make 50 million of anything work together in an orchestrated way without failing constantly is really impressive. And it really is a testament to our ability of abstraction that we're able to do that at all. So before I talk about abstraction, we need to talk about complexity. And I just want to get a little bit firmer of an idea where software complexity comes from. Pennies on the side, so remember, penny for your thoughts. I want you to think about these things. What is software complexity and what can we do about it, right? Concretely, what do you think systems do about it? Think about these two questions a little bit, mull them around, pause, come back. Okay, so what is software complexity? There's a famous book, The Mythical Man Months, written by Brooks, and he essentially broke out two forms of complexity, amongst others, that we might use to describe our system. One is the essential complexity. This is the inherent complexity of a task that we're wishing to perform. So it's mainly a function of the specification for that task's complexity and of the problem that we want to solve, and not of the implementation details or the awkward contortions that we need to do in that implementation to actually succeed at that task. So if we just ask ourselves, can I specify what a task is supposed to be doing? Then there's some inherent and not small complexity in doing so. And that is the essential complexity that is really hard to get rid of in systems. On the other hand, we have accidental complexity, and this is the complexity in task implementation itself that goes beyond the complexity just of the task specification. This complexity is often due to a mismatch between the abstractions that are provided for the code that you're writing and the abstractions that are desired to be able to complete the task. If the abstractions given and the abstractions wanted are deviate from each other significantly, then you're going to need to kind of span that gap in code, right? There's also the notion that there's kind of a friction between all of these bodies of code that you combine together. And that's because you have internal abstractions in some of that code and internal assumptions in some of that code. You have edge cases that are dealing with different aspects of the system. You have special cases that you've inserted into the code, etc. And all of these add to the complexity of the system, especially when we want to add more code. This is one version of accidental complexity in the system. So, of course, the question is, that's not awesome. Can we get rid of accidental complexity? And different people have different takes on this. See the book for kind of links to different takes. But I want to talk about essentially what we do as system designers, right? So the abstraction level that we actually choose to execute some task that we have on can lead to a fair amount of accidental complexity, which implies that maybe we should use a different abstraction level, right? So if we use abstractions that are not a close fit for our task, then it will add complexity. This, in an intuitive sense, is the notion of just using the wrong tool for the job, right? So if we wanted to implement on top of just the raw file system API something like SQL semantics, well, that's going to be a ton of complexity and a ton of difficulty that we wouldn't have if we just used a database, right? So there's this kind of accidental complexity inherent in just using an API in this case that's just far too low level for the tasks that we have at hand. So you might think, okay, that's easy, just use a database. But the second example I think shows something interesting as well, and that's if we want to implement a real-time system, that is a system that can meet deadlines of tasks, the system needs to be predictable. It needs to schedule tasks at specific predictable points so that they can finish their execution in time, right? However, if you're running on an operating system that uses a best effort scheduler, this is just a scheduler that knows nothing about deadlines, knows nothing about real-time systems, just tries to kind of give tasks some share on the system. It's going to be really, really hard to implement that real-time system on that insufficient API. So here's a case where it's really hard to kind of, do the metaphorical equivalent of use a database. It's hard to use some code in between the task that you're implementing and the underlying scheduler, because the scheduler is just a mismatch for what we're doing. We're trying to fit a square peg in a circular hole. So you would really need to replace the entire underlying system if you wanted to do that. So this gets complicated, and I think the second instance shows a pretty salient point, and that's this notion of a semantic gap. A semantic gap is the distance, the metaphorical distance, of course, that an application must try and span between the provided abstractions by the underlying system and the mechanisms that the task at hand needs to perform, right? So there's this gap in both of these examples between the file system API and the SQL semantics that in this case, we can't span that semantic gap by installing a database. However, in the second case, we have some abstraction provided, some sort of a guarantee that we want to provide, and it's not actually possible to span that semantic gap simply because there's a mismatch between the assumptions of the underlying system and those required by the tasks that we need to perform. So this shows us that the abstraction level that we use is really key in what tasks we can perform, and almost more importantly, how difficult it is to perform those tasks that we want to perform. Again, how much accidental complexity it requires. Another factor that raises the accidental complexity of a system is what I'm calling just the weight of software. And the vague notion here is that the larger software becomes, the more likely it is that a change that you want to make will cause friction with some assumption that you've made somewhere else in the system. That assumption might be due to some edge case, some special case, or just some other assumption that you made when implementing the system to simplify the overall system. So as your system gets larger and larger, the probability of having these mismatches is increasingly likely, right? So that means the larger the system becomes, the more difficult it is to do anything with. The more difficult it is to do anything with, the more difficult it is to actually extend it, right? So this boils down to effectively the more assumptions, edge cases, special cases, and what's called the more technical debt that you add to the system, the more future modifications must kind of endure that situation. So this notion of technical debt is something that you incur on code bases over time by taking shortcuts, adding in special cases, etc. Essentially add increasing the accidental complexity of the system. And it's something that makes it more difficult to implement new code, new features. So I think a valid question, given that introduction, is, okay, technical debt sounds horrible. Why not just not do that? Hopefully it's obvious that we can't just get rid of accidental complexity. But technical debt, okay, if that's just due to special cases and all that stuff that you add into your code, why not just not do that thing? So again, pennies on the side. Give me a penny for your thoughts. Think about it and pause, come back. So the idea here is, you're running a company, right? In essence, software is underlying companies that need to have some results. They need features to make their customers happy, and to implement features on the timeline that they're necessary. Sometimes you just don't have the time to design your system properly to try to avoid technical debt. So this is just time pressure is the dominant reason often why you incur technical debt. Also, not skilled programmers and all of these things, but that I would say is one of the main reasons. Okay, so we have complexity in systems. How do we seek to avoid a lot of this, right? So as a system designer, we have a few mechanisms that we use to try to constrain and control the complexity in the system. And generally, the idea is that we want to add structure to the overlying system. And we add structure by using our powers of abstraction, i.e. our powers of basically being a computer scientist. That's what we do. Our powers of modularity and our powers of layering and hierarchy, because modularity is not enough. So I'm going to go through these one at a time with a couple of examples. So abstraction, hopefully it's relatively obvious what I'm talking about when I say abstraction. This is just the idea that we want to provide some higher level interface for resource manipulation and access than what is lower level than that, right? So we need to implement the abstraction on something that's lower level APIs, and we want to provide some higher level interface. What does it mean to be higher or lower level? First, let's go through some examples. So we might think of a file system API as being pretty high level versus raw interrupts, direct memory access, and disk drivers, right? So file systems, yeah, looking pretty good when you compare it to that type of stuff, those types of low-level hardware concerns. And when you're doing web programming, you're typically doing it with, some version of document object model DOM manipulation, right? Just kind of modifying some sort of a tree structure to actually generate the changes in the web page. That's really convenient and really nice, and why a lot of people can do web programming, because they essentially aren't needing to write rasterizing code, compositing code, all of this stuff to actually display things directly on the screen, right? So that is an abstraction that is using those lower level things. Certainly, browsers do all of those things, but it hides all of that detail behind the DOM, right? So at the highest level, and this is kind of the main point that I want you to take away from this discussion on abstraction, is that abstraction is about containing the entropy of more permissive interfaces into a more constrained interface. And this may seem a little counterintuitive. Abstraction we build up as being this powerful, nice thing, but this description is essentially saying that it removes power from the system, right? We take an interface that allows us to do a great many things, more permissive interfaces, and we constrain them to be able to do not as many things. This is often what abstraction boils down to. And it's not intuitively clear why we'd want that, or how that relates, of course, to the abstractions that we see in real systems. So let me go through a intuitive example. There comes a time in every parent's life when, their child needs to go out and drive, and it's terrifying. So, Penny is, in dog years, she is a teenager. So she needs to go out, get a car, drive, get on the road. It's pretty terrifying. But that's okay. I want to provide for her all of the recipes of success for her to drive well. So what we see on the left here is Penny driving a car. We have 4 wheels, top left, top right, bottom left, bottom right. We have the axles connecting them to the main car. And then we have Penny driving the car. And Penny driving the car, she's using a very novel and interesting abstraction for doing so. It's essentially 2 bars connected to each of the wheels. When she wants to turn the car, she simply pushes one and pulls the other. Don't tell her that she doesn't have thumbs. It's a little bit of a sore point for her. But, she's able to do it somehow. And this is nice. We can turn the car using this abstraction. And actually, it's a really powerful abstraction. We can do more than simply steer the car. We can actually stop the car, because if we push both of the bars, we end up creating more friction with the wheels on the ground and stopping the car. So this is actually a really powerful interface. We can do a lot more with this interface than what you and I use to steer a car, right? But of course, we don't use this interface. We instead use a wheel attached attached to some sort of a mechanism that can move the tires for us in a controlled way. We cannot move the tires in as many ways as we could with a lower level abstraction, right? So hopefully this gives you some idea why we want this, right? It's a lot easier for drivers to use this abstraction and to not mess up using this abstraction compared to the previous one. The system itself is undertaking some of the complexity of orchestrating how the wheels get pushed, essentially, right? And is doing so using the steering abstraction. So higher level interfaces allow us to avoid some complexity. That might be considered accidental complexity, the fact that we can do all of those things with the direct bars. So this is a good example why we're constraining the entropy of the underlying system where we have the two separate bars and providing a more constrained interface of the steering to Penny. She's a good pup. Okay. Modularity is also immensely important. Modularity means many different things to many different people, so I'm going to define it in a specific way. Modularity, in essence, is kind of the combination of a notion of encapsulation and information hiding. These are one and the same. The idea that how a certain module implements some abstraction is not public information. It's something that that module can conduct on its own, and the data structures, mechanisms, and algorithms that it uses for doing so are not impacted by the world outside of that module, except through controlled interfaces, right? So this forces what's called a separation of concerns. The idea that within the module, you are implementing some defined functionality, some concern, and outside of the module, they are not able to do the same, to actually implement that specific functionality by directly accessing our data structures, right? So only we are in charge of this implementation. There's a separation of concerns there. This provides strong encapsulation that can be paired with system isolation to increase kind of the reliability of the system. We combine this notion of encapsulation with isolation, and all of a sudden we have a module that guaranteed cannot be interfered with in certain ways from the outside world, right? So we could think of the kernel in a monolithic system as being a module within the system that has this strong isolation. None of the applications can mess with its implementation. Modules also typically implement some interface, which means that they're replaceable. We can take one module that implements an interface and replace it with another implementation, a separate module that implements that same interface. This is typically called polymorphism, or is essentially replacement adhering to the Liskov substitution principle. And it provides a lot of benefits in a lot of systems. It provides adaptability. You can change different implementations if you need to. This is important because it allows us to essentially remove semantic gaps where we need to, right? Provide a different implementation for some functionality that does not provide friction with what your task needs to do, removing semantic gaps. It can provide recovery, dynamic evolvability, because you can dynamically replace the implementation of these modules if you implement it correctly, etc. So modularity, very, very important. However, modularity alone, despite its ability to kind of, by separation of concerns, make it so that we only need to look at this module for some implementation details, it's not enough to constrain or control the overall complexity of the system. This is simply because if we have many, many modules, then and they all talk to each other, we kind of have moved the problem to essentially all of the modules talking to each other. So in addition to that, we use layering and hierarchy, and we'll talk about directed acyclic graphs as well. Layering and hierarchy are essentially ways to take what would otherwise be n squared complexity in the system in terms of the number of modules, because they can all talk to each other, therefore have one module can have n connections to the n minus 1 connections to the other modules. So if you look at all of the connections and the interactions, you end up having n squared interactions. So of course, something that grows quadratically like that is not going to be manageable in the long term as you keep adding modules. So what we want to do is add some structure to that. We want to say, okay, not every module can talk to each other. In a layering architecture, each module can only leverage the modules at the same level as them or layers below. So there are strict limitations on the interactions between modules. And layering is fairly pervasive. We use it in a lot of different systems. This enables us to essentially say, okay, if a certain module has an error, we know what other modules within the system it can impact. It allows us to constrain the complexity because we only have so many interactions between different modules in the system. But a downside is that it can add a lot of pass-through or bypass interfaces. So if you can only talk to the layer below you, but you have some sort of a service request that can only be satisfied by 2 layers below you, the layer below you likely will just kind of pass your function invocation on to the layer below it. This is called bypass. So I said this is pervasive. This is the separation between user level and kernel level in monolithic systems. This is the conceptual separation between the kernel at the lowest levels, OS functionality like GUIs and whatnot above that, browser engines above that, and the tabs for each of your browser windows, each of your browser URLs, right, web pages, above that. So you can see we use layering in a lot of different systems. It's fairly pervasive. But it is fairly limiting, right? If we can only talk to the layers below us and we can talk to any of the modules at our same level, that is maybe not enough of a limitation. So it's one, limiting in that we can only talk to these specific layers above and below. 2, it's not limiting enough because we can kind of talk to any of the modules at our layer without some isolation facilities intruding. So what we actually see in a lot of systems is hierarchical structure. And the idea here is that each module leverages the module below it, like in a layered system, but each module can have multiple children above it. So a hierarchical system ends up looking like a tree instead of just a total order of different modules, right? So the impact of a module error is even more limited in this case because it doesn't even necessarily impact the modules at the same level because we are on a separate branch. In some sense, it'll only impact the subtree of modules that depend on you. Again, you have lots of pass-through interfaces in these types of systems because it's still like a layered system. You still need to go to the parent if you have some sort of a request for service. But it also has the benefit that enables you to customize different subtrees. So essentially the idea is, one subtree could be running some operating system, another subtree could be running another operating system. You've customized each of the subtrees to provide different code and therefore hopefully minimize semantic gaps that you have within the system. So this is again very pervasive. We have virtual machines that essentially are hierarchical systems. Middleware often creates hierarchical systems as well, etc. You can make it so that there are, in some sense, fewer limitations in the system. Any module can talk to any other module, but increase the limitations of the system because you can say exactly who can talk to who, right? So you can make it so that you very explicitly constrain which module can talk to which module by essentially connecting them together in a directed acyclic graph of modules. So we can explicitly say which module can talk to who using this. We will talk about this model a lot because it's what underlies the composite operating system that will be one of the main focuses of the class. But it does really require that we explicitly architect the intermodule relationships. You have to be very explicit about which modules are using which modules. So this can become a little bit of a mess if you aren't very careful with it. Okay, so one question, pennies on the slide for a reason. Why does a general cyclic graph not make much sense? So I explicitly say here, DAG, right? Directed acyclic graph. No cycles in the graph. I will assert that a cyclic graph doesn't make much sense. Think about for a little bit why that might be. Pause, come back. if you have a cyclic graph, it actually makes error handling very difficult, because it's very nice to say, like in a layered system, if a module fails, it probably will not much impact the modules below it in lower level layers, right? In a hierarchical system, you're really only your error as a module will really only impact the subtree of the hierarchical system that you're rooted in, right? But in a directed acyclic graph, you can kind of say the same, right? All of those components that rely on you or transitively rely on you might be impacted by your failure. But once you have a cycle within the graph, everything gets more difficult because it creates this coupling between all of the different modules in the system. So now one of them failing kind of essentially means that they almost all fail, which kind of begs the question why you're kind of using these modules to break apart the system in the first place, right? Okay, so let's just look at some pictures of all of these. On the left, we have a layered system where we have a number of modules in different layers. We have the teal interfaces separating them. We have a hierarchical system in the middle. This looks like a virtual machine, essentially, where we have a virtual machine on the left, virtual machine on the right. And you can see they're running different operating systems. They have different modules within that middle layer. That's something that a layered system essentially cannot do while maintaining isolation between the different subtrees. And we have a directed acyclic graph-based system on the right, where we're very explicitly placing the dependencies between the different pieces of the system, right? Now, looking at these graphs, you can see that yes, the modules are there to provide the implementations that really define how the system behaves and what functionality it has, but the abstractions within the system are really there provided by the interfaces, and it's really important to notate the interfaces within these diagrams because they essentially determine who talks to who over what abstraction. So a key idea that is probably a higher order bit for these slides is simply that interfaces are very, very important. They are the thing that you should spend the most time thinking about and implementing within your system. Why is that? So they can be multiply implemented, which means you can have multiple implementations of that same interface and replace the different implementations with each other. Because they are multiply implemented, that means changing one of the interfaces requires changing all of the modules that implement and depend on that interface. So all of a sudden, there's a much higher burden for changing interfaces in the system than for changing specific modules. So interfaces are key at the design stage because changing them is much more difficult, right? As I said before, interfaces effectively define the system abstractions within the system, and because of that, we need to be very, very careful about how we use them and what they look like. What abstractions do we want to provide in the system matters quite a bit. It matters to try to avoid accidental complexity by providing the correct level of abstraction, i.e. the correct interface, and we need to choose them very intentionally to minimize the semantic gaps. Again, provide the right interface for the right tasks, right? So they also encode the assumptions and error handling of all of the modules that interact with them, both implement them and depend on them. So they encode a lot of important information about what a system concretely can and cannot do, right? What the assumptions are and what the error handling is within the system. So they are absolutely essential because they essentially define this protocol for communication between what's above and what's below, the higher level and the lower level modules. They're often, and they should be, the target of unit tests. So whatever testing regime your system has, it should usually be focused actually on the interfaces themselves. You write the tests to exercise the interfaces, and now your unit tests apply to all of the implementations of that specific interface, not just one specific implementation, right? So they are very, very important because they also usually define the testing interface for the system. Lastly, they are the level at which you typically write specifications. Specifications are immensely important, and unfortunately it would have taken 4 classes to go over them properly, so I'm just not going to go over them much in this class. But they are simply the idea that we need to describe the functionality of some interface, of some abstraction, and that is the specification. We want that description to be at a relatively high level relative to the actual implementation of the module itself, and because we can have multiple modules that implement an interface, it becomes very important to have that specification exist and be relatively concise, because each of those modules needs to implement it specifically. So because of all of these things that are relative to the interfaces in the system, it's really, really important that we get them right. They, in some sense, define how we manage the complexity in the system. So to say that interfaces are the core of system design is an understatement. And a lot of the code that we read within the class is going to be focusing mainly on interfaces in one way or the other. So this isn't the focus of the class, but I also want to talk a little bit about a little bit of a pivot to how within a single module, thus the circle on the right, how do you actually control complexity, right? And there are many kind of high-level ways to think about this. I go over a few in the book, but they all basically boil down to the notion that you want to keep it as simple as possible. There's often an impulse, especially amongst people who are learning computer science because it's so amazing, to overgeneralize, right? You want to write code that can apply to every situation, but often writing code that applies to exactly the situation that you need it to is the right thing to do. Later, you might generalize it when you realize that you need to, it needs to be general across multiple applications. But overgeneralization goes a long way to making systems immensely complicated. So generally, you want to avoid that. Optimization as well is something that requires you to replicate code paths, contort the code to make it faster in certain ways that make it more difficult to read. Optimization is something that you just don't want to do in general. It's something that you want to do where you know you need it, but you need to intentionally know that you are doing so at the cost of the complexity of the system, right? So these are kind of 2 general guidelines for kind of keeping your implementation as simple as possible. You can find many others on the internet. Additionally, I would say that one of the great ways to actually control and constrain the complexity of your system is actually to have pervasive testing of the interfaces and abstractions within the system. This gives you a lot of confidence within the system for your implementation and allows the replaceability of different components in a much more trivial way. So if you do implement something simply that doesn't work in many cases, maybe it's not optimal in terms of performance, maybe it doesn't generalize across some cases that you want it to, that's fine. You can write some tests for it, make sure that it works. Maybe it's not fast, maybe it's not general, but it works. And then once you have the unit test working, you can provide different implementations of that module that optimize for other things when you need to, right? But simplicity, number 1, and then allowing us to test the system relatively easily, number 2. Okay, so what have I talked about so far? In this lecture, I talked essentially about the fact that complexity is horrible, and complexity comes with a massive weight of software, and it comes with a lot of structural problems that we might have within the system for accidental complexity. So what can we do? We've talked about 3 different techniques: abstraction, modularity, and adding structure, layering, hierarchy, DAGs, whatever. These are essential when you're designing an overall system. You don't have a choice of doing them. If you want your system to work, you essentially have to do them because our brains cannot handle complexity once it goes beyond a certain point. And I've talked about very briefly the idea that we essentially want simplicity within modules and to deviate from that simplicity intentionally and hopefully rarely, right? And one of the, again, the higher order bits of all of this is the idea that interfaces essentially encode abstractions within the system. So they are fundamental and they are where most of your design time should usually be spent. So as we go through the class and as you investigate many different code bases, I want you to think about the abstractions and the interfaces as one of the most important things, and then dive into the code from there. All right. Thank you very, very much. Hopefully this was fun. I will see you soon.